Welcome everyone to yet another exciting episode. I am your host and my name is Shaunak, and we have a very special guest joining us from a very distant place, Professor Justin Clark Doane. Professor Clark Doane is an associate professor of philosophy at Columbia University, and his work delves deep into the realm of metaphysics and epistemology, but his influence extends far beyond the ivy covered walls of academia. He is an honorary research fellow at the University of Birmingham in UK and an adjunct professor research associate at Monash University in Australia, and has even graced the prestigious Institute for Advanced Study in Princeton as a periodic visitor. His expertise spans a vast array of captivating topics, from foundational issues in the philosophy of mathematics to the intricate interplay between reality itself. Professor Clark has authored enlightened texts such as Morality and Mathematics and Mathematics and Metaphilosophy, along numerous thought provoking articles that challenge our perceptions of truth and knowledge. Without further ado, let us give a warm welcome to Professor Justin Clark Doane. Professor Clark, thank you so much for joining us today. It is an absolute pleasure to have you here, and who is joining from, I think, Wisconsin, USA.
Thanks a lot for having me. Yeah.
Thank you very much. As I just wanted to tell you that this is a much awaited podcast, and I'm thrilled, excited, and honored to get somebody from the University of Columbia, New York, as a professor of on the philosophy of mathematics. Professor, I would initially want you that if you can give us a brief introduction, actually, on the work that you do and what is the central area that you kind of work into.
Thanks. Yeah, thanks a lot for having me. The work that I do generally is, as you said, in what's called metaphysics and epistemology, and these fancy words just have to do with metaphysics has to do with trying to be very clear about the most fundamental assumptions we make in theorizing about the world. So that intersects in obvious ways with the foundations of physics, for example. And then epistemology is that's just a word for the theory of knowledge. So it's the theory of what we know and how we can know what we think we know. And the specific areas that I've been most interested in are the areas that are, you might think, most puzzling at first glance. So math is, of course, a paradigm here. So, I mean, think about mathematics, pure mathematics, for a few minutes, and I hope that you'll feel puzzled. It's something that, on the one hand, seems to be, a paragon of certainty. So if there's anything that we know, it's that there are infinitely many prime numbers, for example. But on the other hand, the way we determine our conclusions is by sitting down with pencil and paper and just thinking. On the third hand, math is indispensable and ubiquitous in the empirical sciences. So we sit down with pencil and paper, we arrive at something certain about a realm of numbers or tensors or, sets, and then that finds application in the world around us, often in a way that seems, as I say, indispensable, unavoidable. So math is a great example of the kind of area that I'm especially concerned with, and the general name for areas of this sort is a priori areas. So there are areas that we seem to arrive at our conclusions just by thinking. There are less salient examples of the same sort of thing. Philosophers of math and logicians distinguish math per se from logic. So if you think just very simply about, say, like the axioms of Euclidean geometry, those are non-logical principles. And in a regimentation, though, today, like Hilbert's in the early 20th century, you would then assume as a background, without even stating them usually, principles of logic which tell you what you can derive from those non-logical principles. So logic is its own subject of metaphysics and epistemology. What is it about? How do we know it? What's the relationship between logic and the empirical world? There's also what's called modality, the theory of possibility and necessity, and that turns out also to be, on the one hand, something that we arrive at conclusions just by thinking, and it can be treated mathematically as well. But again, it's central to our theorizing about the empirical world. So when you think about a state space of a physical system, for example, or a configuration space, these are once again counterfactual ideas. When you say, how could a physical system evolve that started in a certain initial state, that's a counterfactual idea. So so the final area that falls under this umbrella that I'm interested in, and I'm interested in the relationship between it and the other areas. Somebody might think that there is no relationship between it and the other areas, but is the area of normative thought. So thought about what you ought to do, how you ought to live, what you ought to believe, what's good and bad, things that seem totally different than on its face math or logic or, you know, counterfactual reasoning in the physical sciences. So the big picture, to answer your question, is I'm interested in metaphysics and epistemology, and especially metaphysics and epistemology as they concern what are called a priori areas, the areas that where we arrive at conclusions just by thinking.
Okay, great. Thank you for this great introduction. Now, my question, Professor, would be, because this is something really interesting. Now, you were talking about the Euclidean axioms, or later we moved from into Euclidean to non-Euclidean axioms. Now, concerning the philosophical principles, now, say, for example, we observe certain things. For example, this room, etc., and we saw there's a bulb and there is something which is glowing, and based on that, there's a hard pencil that we take over, and based on that, we do the experimentations. So based on the experimentation, we then prove that, okay, so if this happens, what you were telling, logically this would happen. So what I'm trying to understand is that these numbers, now, say, for example, 1 plus 1 equals to 2. Now, is it something you would call an assumption based on observation, or is it something intuitive? Why it is generally has to be 2? Why it is not 11? I mean to say, how do the philosophy of mathematics arrive to this conclusion?
Great. Okay, so I mean, to translate your question into the language that philosophers use, what you're asking is whether math is a priori, as I've been describing it, or rather a posteriori. These are just Greek. These are just fancy words for saying, is it something that we can know just by thinking, or is it actually an observational idea that just like forces mass times acceleration or something? In other words, why think that math isn't just maybe a very abstract empirical science? And the idea that math is an empirical science has in fact been proposed at different points in the history of philosophy. The most famous advocate of this view is probably John Stuart Mill, who thought that literally things like 2 plus 2 is 4 are enumeratively inductive generalizations looking at collections. And we've, whenever we've seen a collection of 2 things and a collection of another 2 things, we've seen a collection of 4 things. So we conclude that 2 plus 2 is 4. Frege, Gottlieb Frege, the founder of logic as we know it today. So when one talks about what's called first order logic, but just mathematical logic as the subject is understood today, Frege had a very famous and scathing criticism of Mill's empiricism about math. So that's to say that Mill's view that math is in fact an empirical discipline, just like ordinary claims of the physical sciences. And I'll give you a few reasons why Frege was was unsatisfied with this point of view, and we can talk about, you know, whether or not this is a legitimate these are legitimate criticisms, but I'll give you a few reasons to think that indeed math must be a priori. It must not be the kind of thing that we arrive at by experiment. So the first thing that you can observe is that, let's take already the simplest mathematical theories and assumptions that we use. So take the axioms of piano arithmetic. So those of you who are familiar with piano arithmetic, there's an axiom that says that there's a number 0 that exists. There's an axiom that says that if the successors of two numbers are the same, then the numbers are the same. There's recursive definitions for plus and times. And then there's what's called the induction schema, which is a meta-linguistic claim, which says that for any formula in the language of arithmetic, if the formula is true of the number 0, and it's true of the successor of a number whenever it's true of a number, then it's true of every natural number. Okay, so one immediate consequence, for example, of the piano axioms is that for every natural number it has a successor. For every number there's a number after it. But if you think that those axioms were arrived at or could be arrived at empirically, then you can ask yourself how that could be. I mean, we have maybe it's the case that for every collection of pebbles, when we've seen a collection of n pebbles, we've seen a collection of n plus 1 pebbles, or we could imagine adding a pebble or something. But that's a long way from saying for every natural number it has a successor. I mean, that's a long way from saying there are infinitely many numbers. And when you turn to something even as rudimentary as like Euclid's proof that there are infinitely many prime numbers, I mean, that doesn't seem to be the sort of thing that has the status of an empirical conjecture that we could learn is false. I mean, if that were the case, if arithmetic were an empirical discipline, then and mathematics generally were an empirical discipline, then the mathematicians should really change their methodology. They should be in constant contact with the experimentalists. They should be checking whether or not, their most recent theorems have found any application. They should be agnostic until they do. But that's not at all the methodology. That's not at all the methodology that mathematics or logic uses. It doesn't seem to concern itself with the empirical world. I mean, famously, Hardy, in his book, A Mathematician's Apology, celebrated the lack of applicability of his specialty, number theory. Of course, it turned out later that number theory has great application in cryptography, but he didn't know this. So the kinds of criticisms Frege had is just, if you put together the following observations: the methodology of math does not at all conform to the idea that it's an empirical science. Secondly, the level of certainty we have about math does not at all conform to the idea that it's a speculative conjecture on the world that could turn out to be false. And then finally, the necessity of math, the idea that it couldn't have been any other way. Like it's not that, there's a nearby possible world that we just don't happen to inhabit where there aren't infinitely many prime numbers. This was Frege's thinking. So I would just add to those points one more, which is that to even do experiments and experimental science, one assumes a bunch of math. I mean, it's not like the math itself seems to be on trial when you do an experiment. You use the math to see what the experimental result even is. So the statement of an empirical result will generally be up to its ears in mathematical language. So these are just some of the reasons, to respond to your question, which is a completely fair question, why philosophers tend to assume that math is not, the claim that there are infinitely many prime numbers is not like the claim that there are gravitons. It's not a empirical conjecture on the world in the same way. Now, that's not, beyond dispute. And this is one of many things that philosophers do discuss. I won't continue with the filibustering, but I'll just say that the philosopher W.V. Quine, for example, developed a much more subtle and nuanced conception of how math could be empirical in the mid-20th century. And I don't think myself that it works at the end of the day, but it's not something that you can dismiss as easily as Mill's view, for instance. So that's the short answer to your question.
Okay, thank you, Professor. That was a very lucid explanation. Subhasri Bhattacharya, one of our subscribers, is telling me, Subhasri, I achieved my master's degree in philosophy, and ethics was my special paper, which is my favorite topic till now.
That's great. I'm happy to hear that.
Yeah, while we have a question, Professor, general question. Deepani is asking, sir, is concentration must need for a master of mathematics?
So is the question, if you want to specialize in philosophy of math, do you need a master's in math? Is that the question?
Yes, or in general doing mathematics, she is asking that, do you really need to concentrate hard, and is concentration important?
I see. Yeah. Sure. I think concentration is essential. But I don't think in that way math is different than any other subject. I mean, I think to do any subject, any of the standard subjects at a high level, unfortunately, you just got to put a lot of work into it. It'd be nice if there were a fast track, but concentration I think is essential. And and philosophy, being as it is so concerned with distinctions and precision and the subtleties of language, including mathematical language, I don't really think there's any avoiding concentration and wrestling with distinctions that one might not have been inclined to make before.
Absolutely.
Yeah.
Absolutely. I'm coming to another question, Professor. But before that, I have one question which kept me busy.
Sure.
I mean to say, we have got an answer a little bit from the Eastern philosophy, but I want to know your views. Now, what we know is that in arithmetic, whenever we add or we subtract a number, say, for example, whatever the number, we get hold of another number. Addition gives you another number, subtraction gives you another number. But considering the number 0, if we add 0, it again gives the same number itself. When we subtract 0 from 0, it again gives the number 0 itself. So there is a kind of an iteration in terms of 0 with addition and subtraction, which in case of other natural numbers, we really don't have. How do you look it into the philosophical point of view, that why it is that it is typical to 0 that gives back to that number, whereas other numbers, any arithmetic operation would result into another number?
Yeah, I mean, that's a great question, and I don't know if there's a satisfying answer that's not just more math. So, I mean, one thing to point out just historically that's kind of interesting is that 0 was relatively late on the scene in many societies, and in fact, I think it's in Euclid's Elements, the numbers, quote unquote, were supposed to start at 2. So 0 wasn't a number, but neither was 1. Multiples of 1 were numbers, and the concept of 0 was not well understood. So there is something I think that historically mathematicians have found puzzling and awkward about 0, but arguably the process of math has just been the process of generalizing an idea more and more. So you have the positive integers, and you already said that if you subtract 2 numbers you get another number, but of course that's not correct. If you start with the positive integers and you subtract 4 from 2, you don't get another number. So you already have to expand into negative numbers. And then once you've got negative numbers, it's very natural to have a point between the positive and negative numbers. And and once you want solutions to equations, it's very natural to introduce irrational numbers and the imaginary numbers and so forth. So arguably the introduction of zero can just be seen as a special case of that kind of introduction of an ideal object that simplifies what would otherwise be a messier arithmetic. I should say that there's another example of this that mirrors the phenomenon you're talking about, which is the introduction of infinity as a number. Right. So before the late 19th century, infinity was not taken to be a number. It was taken to be just, it goes on forever. Infinity is just foreverness or something. But George Cantor is the inventor of the theory of transfinite sets, and he introduced the idea that you can do arithmetic with infinities understood as numbers, and this doesn't get trivialized because it turns out in a well-defined sense there are different sizes of infinity. So, for example, the size of the natural numbers is strictly less than the size of the real numbers. And the question of how much less it is what's known as the continuum question. And famously, that was proved that was Hilbert's first question. In the turn of the 20th century, David Hilbert listed what he took to be the most important questions of the 20th century. And the first on the list was, is it the case that the size of the real numbers is the next greatest size after that of the natural numbers? More carefully, this assumes the axiom of choice, this formulation. But talk about philosophy of math. It turns out that it's not just that nobody's proved or refuted that, the continuum hypothesis. In the mid-20th century, Kurt Gödel, and then Paul Cohen, in a combination of results, proved that if standard mathematics is consistent, you cannot prove the continuum hypothesis and you cannot refute it. So standard mathematics does not resolve the most basic question you can ask about different sizes of infinity. But anyway, the point was that infinity itself, understood as a number, has this feature that you were talking about. If you take infinity and you add infinity to it, you get infinity. If you take an infinite set and you remove an infinite part of it, the result is still infinite. Can still be infinite. So I think I don't think that there's a super informative answer to your question, except to say that the process of introducing zero, which behaves differently than other numbers, is a lot like the process of introducing infinity or I or negative numbers, which is kind of like the most characteristic activity of mathematics: generalization, introducing ideal objects that simplify some broader arithmetic.
Okay, thank you. That's one. We have got an interesting question coming up from Rajvardhan. So he's asking, can mathematics one day evolve to a level that it can answer relative to morality what is right or wrong? My question is in light of game theory, which has influenced decision making.
Yeah, I mean, the role of AI in mathematics and theorizing more generally, including even philosophy, though it hasn't really entered the scene in philosophy in any super interesting way yet, is of course an actively discussed topic. This is a very timely question. In the case of pure mathematics, already AI is starting to play an important role. So in the 70s, for example, we had our first really dramatic illustration of what kind of role AI might play in math, and that was in the proof of what's called the four-color theorem, that any planar map is four-colorable. And what happened with that is that there was a point in the proof where there seemed to be no way around checking a zillion cases, many more cases than any human being could check. And so for the first time, as far as I know, in a proof of a major theorem, a computer was used to check the zillion cases, and no referee of the paper could go through all those cases. So meanwhile, no proof not using a computer essentially has been produced. So on the one hand, the four-color theorem is taken to be proved. On the other hand, there is no proof that someone can hold in their head, in the way that every other proof, even for Mott's last theorem with its Baroque proof due to Wiles, it's not the kind of thing anyone who specializes in that field has from beginning to end in their head. They have this black box part of the proof, which is this is where you feed it to a computer and you can trust the computer. So one point just to say is that with the rise of automated theorem provers, proof checkers, proof assistants, math is almost certainly going to take on a different flavor. And this, I'm talking at the moment now about pure math, and I haven't gotten to your question about morality. So what about morality? I mean, morality, there's a similar issue. It might seem like there's a question in the moral case that doesn't arise in the mathematical case, but actually there's a very strong analogy. So in the moral case, right, you ask, will AI get to the point where it can answer moral questions for us? Well, it's helpful to think through that question and what it would mean for AI to answer a moral question for us. You got to program the AI. You got the AI doesn't come out of nowhere. It starts with principles. And so when people talk about, for example, programming self-driving cars and how to respond, in circumstances where a kid is running across the street, but I don't know, that if you swerve right, you'll hit 5 elderly people or something. The point is that human beings are the ones who have to come up with the most basic principles that the AI can then think through and systematize, and it can worry about maximizing utility if that is one of the desiderata of the program. But you get out what you put in, and the ones who decide what to put in are human beings. And the same thing is true, actually, though this is less obvious, in the mathematical case. So in the mathematical case, something that is once again coming to the forefront that most mathematicians have been, I think, happily, ignorant of for about 100 years, is that, math does rely on axioms, principles about what kind of functions we're allowed to form, what kind of sets we're allowed to form, and what kind of reasoning we're allowed to use. And we think we just know what the answer to that is when you start in math class. I mean, in math class, it doesn't start with it doesn't start with here are the axioms and here are the laws of logic. You may or may not at some point as an exercise be told, just kind of like, just not to think through, but just sort of to learn. Here are the axioms of propositional logic and quantificational logic, and here's the axioms of ZFC set theory. But the point that, you could question those, and there are alternatives to those, and people actually do debate those, is not raised in a normal mathematics class. But when you start thinking about programming AI as proof checkers, proof assistants, and proof generators, you have to take a stand explicitly on what axioms are you going to program that machine with. And one of the interesting things is that some of the most successful AI platforms today are actually not based on classical logic. They're based on what's called intuitionistic logic, where what's called the law of the excluded middle is no longer valid. The law of the excluded middle says that for any proposition P or not P is a logical truth. So you can always assume that for free. Any sentence S, you can always write S or not S. It's got to be one of those two. In intuitionistic logic, that is not taken for granted as a law. It's not that it's saying that it's not true that, you know, either some sentence is the case or its negation is the case. It's saying that that's not free. If you want to establish the disjunction of a sentence and its negation, you have to establish one of the disjuncts. So so the short answer to your question is, I think it assumes that AI can do more than it can, that it has an ability that it doesn't. AI starts from a program that we write. And that program assumes laws of logic, laws of mathematics, and whatever. And there's no getting around the debate you have to have outside of the, outside of the program among human beings about what axioms to accept and what laws of logic to use. And unfortunately, you know, those debates have not gone away. They've just gotten quarantined. So as a matter of practical, as a practical matter, the mathematical community around the 20s or 30s landed on a set of axioms called the ZFC axioms and assumed something called what's called classical logic. And then they didn't kind of worry about it anymore. The people who worried about it were the logicians and the philosophers. And we continue to worry about it, but it might start to be again that everybody has to worry about it. Everybody has to worry about it now with the rise of AI. And that's very much like the moral case and programming self-driving cars. Absolutely. So the answer to your question, the answer to your question is I think it's a headache. I don't think there's a simple answer to that.
Simple answer, right. I have got a question from Rajkumar Chatterjee, but before that, Ashirvad Garg is asking you, sir, can you recommend some book or lecture playlist on the philosophy of mathematics? I'm going to see if somebody wants to start as a student.
Yeah. Well, so I don't know playlists. I'm not up on that, unfortunately, but I can certainly recommend some books. So there's a sort of Bible of philosophy of mathematics up to the 1980s. So it covers the most important papers from the around 1880 to 1980. And that's sort of the early 20th century was the sort of glory days of the first iteration of the philosophy of mathematics. But a lot of interesting stuff happened then later in the 20th century. And the book is an edited volume of translated into English texts. Some of them were English, but some of them weren't. Called the Philosophy of Mathematics by Paul Ben Asaraf and Hilary Putnam, who were both philosophers. Hilary Putnam actually contributed to resolving Hilbert's 10th problem. Once again, in a characteristically philosophical way, Hilbert wanted an algorithm for checking whether or not an arbitrary Diophantine equation has solutions in the integers. Turns out there is no algorithm. Right. So that's what was proved. But anyway, that's the maybe book to start with. That's a great book. It's not easy, but it's got a great introduction that'll help you, I think, get a grasp of what kinds of questions are at stake. There's other books, but I would start there.
Okay, great. Rajkumar Chatterjee is asking, sir, is infinity just a concept?
Yeah. I think the most productive way to answer that question is not at first just saying yes or no. Because of course, any answer I give you, yes or no, is going to be very controversial. For the purposes of thinking through the question, I think the most productive way to think about it is there any special reason to think infinity per se would just be a concept? In other words, if you think infinity is just a concept, are you thereby committed to thinking, say, arbitrarily large finite numbers are just concepts? So, I mean, imagine, for example, that there are only finitely many particles in the universe, which, as far as I know, is consistent with what we know. It's possible. Now, certainly, as a conceptual matter, we can imagine the number that is the successor of the cardinality of the universe, the successor of the number of things in the universe. Is that just a concept? Well, if it is just a concept, that's going to be a problem, because we make all sorts of statements that have unbounded quantification over the natural numbers. They talk about all the natural numbers, not just up to whatever, however many particles there happen to be. And we also think that those facts are not just somehow conventional, depending on human beings and whether they happen to exist and have invented the concept of a bigger number. If we were all to die tomorrow, hopefully we don't, but if we were, it would still be the case, most people would assume, that there are infinitely many prime numbers, for example. Moreover, to complicate the problem further, the physics that you presumably don't think is just a concept is up to its ears in mathematics, and moreover, infinite mathematics. It's up to its ears in calculus, which assumes infinity as a completed idea, so arithmetic, piano arithmetic, does not assume the existence of an infinite set. It assumes that there are infinitely many things, but whether you can collect them, that's a further issue. The claim that you can collect them is called the axiom of infinity, and it's one of the axioms of standard mathematics. It's the claim that there is an inductive set. That axiom is required to do analysis, mathematical analysis, calculus, the kind of math that's, left and right in ordinary classical physics, set aside quantum mechanics. So I think the most productive question to respond to your question with is, well, if you want to say that infinity is just a concept, how are you going to get away with saying that the physical world isn't just a concept? How are you going to get away with saying that arbitrarily large finite numbers aren't just concepts, and so forth? So if you're comfortable saying that all that stuff is just concepts, then be my guest, say that infinity is just a concept. But if you're not comfortable saying that, then I think you got to say, no, infinity is not just a concept. It's as real as the natural numbers.
Absolutely. I would say thank you. It's turning up to be very interesting. Now, Singularity have got a question, Professor. Do the set of all natural numbers are bigger than the set of real numbers?
No, the set of real numbers is bigger than the set of natural numbers. That's called Cantor's theorem. But the question, which is not just we don't know the answer, but you can prove that given standard axioms and anything people have proposed as potentially reasonable extensions of those axioms, if they're consistent, you can't prove it and you can't refute it, is how much bigger the set of real numbers are than the set of natural numbers. And it turns out that there's actually tremendous freedom on that question. So you can consistently add almost any answer you want to the question of what is the cardinality of the real numbers. That is to say, what's the infinite number of the number of real numbers? We know it's bigger than the infinite number of the number of natural numbers, but how much bigger? You can basically say whatever you want, and you won't end up with a contradiction if ordinary math isn't contradictory. So getting back to the question that was the previous one, which is, is infinity just a concept? I mean, one way of thinking about that is it somehow just a vague idea, or is there a fact out there waiting to be discovered about the nature of infinity? Well, a very real question is there a fact of the matter about the size of the size of the real numbers? Mm-hmm. Given that you can't prove it and you can't refute it, whatever fact you claim exists. And this gets us to, questions that we were discussing earlier about what is the nature of mathematical truth, given that it depends on axioms. And the axioms, there's freedom as to what to assume. These are not God-given axioms. The world did not come down and tell us that the axiom of infinity is true. So the relationship between truth and proof is central to the philosophy of math and central to the question of, whether math is an objective discipline, discovering facts like physics takes itself to be.
Right, thank you. I have one question, Professor, but before going to that question, I would like to just tell our viewers on a case, which definitely you, Professor Justin Clark, but I would like to give a little bit view and then I will come to the question. The R
Yeah.
versus Dewdley and Stephen case, which is known to us as the lifeboat case, is a tragic incident where four men were stranded in a sea. Facing starvation and dehydration, Dewdley and Stephen killed and consumed the cabin boy, Richard Parker, to survive. When rescued, they were charged with murder. The case raised ethical dilemmas about the limits of survival, necessity, and the morality of taking another life to save oneself. Dewdley and Stephens argued they had no choice but to sacrifice Parker, while the prosecution maintained such an fact is, I would say, such an act is something unjustified, and the case ultimately led to legal precedent regarding the defense of necessity in extreme circumstances. Now, considering this, Professor, if I consider you to be the judge and you being a mathematician, I'm assuming, let's say, for example, if we talk of morality, if I'm a mathematician, I know what is the right answer, what is the wrong answer, and I would take the case of R versus Dewdley, Dewdley and Stephens. Would you bring the mathematical morality in order to judge the murder of the cabin boy, or would you take it in a different way, considering the ethical part as well as considering the mathematical morality that we are just talking about?
Yeah, so I mean, I think what you're asking is, look, in the math case, we think there's right answers that you can prove and settle. In this is a prime example of an ethical dilemma where it seems hard to say there's a right answer that you can prove and settle. I mean, nobody has proved or settled it. So isn't that a essential difference, or is there a way to somehow show that they're the same kind of thing? So I actually think that there's a way to show they're the same kind of thing, but not in the way that you might suppose. So rather than thinking that there's some kind of algorithm for settling the ethical case, I think that the idea that there's some sort of algorithm for settling mathematical cases is exploiting the word settle in a misleading way. So, one thing that starting with Frege, philosophers and logicians have gone to great pains to do that's really useful when trying to think about the nature of mathematical truth or truth in any area, is to distinguish exactly what assumptions one makes when one proves something from the proof itself. So let's take a case where we think there's a right answer. Suppose somebody asks you, how many prime numbers are there? Well, you can appeal to Euclid's proof that there are infinitely many prime numbers. For every prime number, there's a greater prime number, and it's a lovely proof that shows you sort of constructively how to construct the prime number given a number. Well, okay, if you were to formalize that or regiment that or make that perfectly precise and rigorous, what would that look like? Well, what it would look like is you would have a first order formulation of the Peano axioms, and you would have then built in or background to those axioms the axioms or principles of classical logic. Now, as a matter of sociology, in math, we don't ask the question normally, are the Peano axioms true and is classical logic correct? That's not a normal mathematical activity. In fact, most mathematicians don't probably even know how to formulate the Peano axioms in the very specific first order sense that I'm mentioning. Logic is a sort of peripheral discipline that most people, you don't even have to take a course in logic, because it's kind of theoretical and fringe in a way that differential geometry, for example, is not. So the problem is, though, that there is debate about, for example, the induction schema and whether or not that schema holds for every predicate or only, say, bounded predicates. So, I mean, a good example, if those interested in a heretical development of arithmetic might look at Edward Nelson's famous monograph, Predicative Arithmetic. I think it's freely available online for download. He was a mathematician at Princeton until he died recently. Similarly, we've already talked about non-classical logics that are assumed in in proofs, like the proof of the classical logic is the logic that's assumed in proofs like the proof that there are infinitely many prime numbers. And we've already talked about the existence of non-classical logics. It's not just that there's intuitionistic logic, there's what's called paraconsistent logics. And paraconsistent logics, it's not that they say that it's not that they say that the law of the excluded middle is not valid. They say there can, as a matter of logical possibility, be true contradictions, claims of the form P and not P. Now, anybody who knows a little bit of logic will know that in ordinary logic, from the claim P and not P, you can derive anything. Because if you imagine I have P and not P, well, then I have P, and I can always say P or Q, that's weaker, but I also have not P. So I have P or Q and not P, so it's got to be Q that makes that whole thing true, but Q is arbitrary. So from P and not P, it seems like I can derive anything. So obviously paraconsistent logicians reject some of the inference rules that I just used. The specific inference rule that's normally rejected is what's called disjunctive syllogism, that lets me go from P and not P, P or Q, not P, to Q. But the point is, all these things are debated. They're actively debated. The debates are quarantined. As I said before, most people are not even aware of the issues. In fact, I would be interested to hear from the audience how many people have even heard of paraconsistent logic. It's not a normal mathematical activity to even be exposed to this. But that doesn't mean that there's not the arguments and there aren't the debates. And so here's the issue, to get back to your question. In fact, if we're being honest and we're comparing apples to apples and not apples to oranges, we have a similarity with the ethical case. There doesn't seem to be an algorithm for settling the question of whether there are infinitely many prime numbers categorically. What we can settle is, if you assume the Peano axioms and you assume standard logic, you can derive that there are infinitely many prime numbers. But what about the status of the Peano axioms and the status of standard logic? Is there an algorithm for settling whether those are right? No. Unfortunately, it's just philosophy. You just got to do the same old thing that we do with all the philosophical questions. And there's not a simple, there's not a crucial experiment. There's not a way to settle the issue in the sense that will convince everybody of the result. So I think that actually math and ethics, you're absolutely right to highlight this apparent radical difference between math and ethics. But I think under a microscope, the difference is actually methodological and not a matter of principle. The mathematical community has decided to focus on what follows from some axioms that, we have all decided to use. Whereas in the ethics case, we want to know what axioms are true. But those are two different issues.
Yeah, I get it. I mean to say, this is really something very serious. I mean to say, you really, it's mind-boggling. And this brings to another question, which I know, Professor, would be a little bit out of the track to ask you. But I mean to say, we have a good discussion. We have many people are watching this podcast. We have heard about Grigori Perelman, the man who proved the Poincare conjecture, and the person who declined the Millennium Prize, all the great prizes which would have made him a great person. Now, if you go back, there are a lot of arguments regarding a lot of issues that Richard Hamilton was the inventor of this Ricci flow, and he was not really credited. But I want to hear, because you are from one of the most reputed organizations in this entire world, Columbia University. You as an individual, what would you think? What would be your philosophical reflection on this rejection of this Millennium Prize by Perelman? Was that an ethical issue or an ethical dilemma which made him refuse this one?
Yeah, well, so I should say I don't know him at all, and I don't know why he did this, but I do know, there are some great mathematicians who have earned and accepted some of the most prestigious prizes, who are nevertheless frustrated at the way in which recognition is given in math. So it's not a new idea that math is cumulative and everybody is building on everybody else, and yet the person who makes that last move and proves the theorem from some lemma, even if the heavy lifting was the lemma, will be remembered, And of course, this is not peculiar to math. If think about special relativity. I mean, I think anyone on the street who thinks of special relativity could name Einstein. Could they name Poincaré or Lorentz or Fitzgerald or So and similarly with Nobel prizes. I mean, I know Kip Thorne, for example, has made a real point to emphasize all the people who played a role in the detection of the black hole that we've now taken a picture of, and of all of the things that he got, the things that he was recognized for. So there's a general issue in science, but not just science, in philosophy too, less so in philosophy maybe, but it happens in philosophy too, which is that the reality is it's a communal enterprise, and we all are relying on each other all the time. And it's a little strange to give all the credit to the person who just happens to go through the finish line. And so it could be that Perelman was sort of protesting that practice. I don't know, because as I say, I don't know him and I don't know his reasons, but, I definitely wouldn't want to suggest, I definitely wouldn't want to pretend to be an ethical authority on this matter, but I don't think it's crazy to have that concern and to feel like the incentive structure in math actually favors people, hiding their work or, jealously seeking out a particular result rather than one that might be more fruitful long term, because that will get more media attention or something. I mean, those are legitimate concerns. Somebody who I think has spoken to this, who's among the most eminent mathematicians living, is Langlands, the author of the Langlands program at the IAS, and he periodically complains about the sort of jealousy in math. He's of course someone who doesn't need to be jealous because he's doing just fine. But I think there is something to be frustrated about there.
Thank you. It's already 53 minutes, but I have a few more questions, if you can permit me. I know it is very early morning over
Sure.
there.
Oh, it's fine.
That is, your favorite subject, if you can just emphasize, because there are people who might not be knowing the depth of that. So if you can explain in a little bit simple language, why Gödel's incompleteness theorem is so important and the impact it had on the philosophy of mathematics.
Yeah, good. So to explain that requires a tiny bit of history, but not a ton. So I mentioned Gottlieb Frege, who arguably invented quantificational first-order logic, which is the logic that's in the background and assumed in all of mathematics. And in fact, today, it's assumed in all of science. Whenever one talks about, could you formalize this theory rigorously? What they mean is, could you write it in a language like Frege's? So Frege was a philosopher at the end of the 19th century who came up with this. Charles Sanders Peirce was an American philosopher, had some of the ideas, but he wasn't nearly as clear about the philosophical issues as Frege. So anyway, around the same time, the philosopher Bertrand Russell was developing a program which was very much in keeping with Frege's, and the program is known as logicism. And logicism is the idea that all of math can be reduced to logic. Now, what that means is that you can define all mathematical concepts using only logical concepts, and you can derive all of mathematical truths using only axioms of logic. And so Frege had gone some way towards arguably doing this. And one of his axioms was what's called Basic Law 5. And Basic Law 5 in contemporary language says that whenever you have a predicate or a condition, like a property, you can collect the things that satisfy that property. I mean, think about how you think about properties in ordinary math classes. You just think of them as sets of the things that have the property. Like, what's the property of being even? It's the set of even numbers. So whenever you have a property, you can collect the things that have it. And if the property is some nonsense property, like being non-self-identical or something, that's fine. The set of things having it is then the empty set. Well, Russell pointed out actually this principle, which Frege thought was a law of logic, is not just not a law of logic, it's actually inconsistent. And the reason is, think about the set of things that don't contain, the set of sets that don't contain themselves, or the property of not containing yourself. So if I have the property of not containing myself and I have basic law 5, I can collect the set of sets that don't contain themselves. Okay, well, now it either needs to contain itself or it doesn't contain itself. There's only two possibilities. And if it does contain itself, then by what it is, it doesn't contain itself. And if it doesn't contain itself, then by the condition for being in it, it contains itself. So there's no consistent way to answer the question of how that principle applies to the property of not containing yourself, the set of all sets that don't contain themselves. So Frege's version of logicism, the idea that math is just logic, does not work. However, Russell thought you could still develop this idea. And he and Alfred North Whitehead then pursued a ambitious project to reduce all of math to logic, but not Frege's logic. And this was called, this resulted in the 3-volume set that so few people bought that they had to self-finance this thing, called Principia Mathematica, the same name as Newton's Principia Mathematica, except this thing is much harder to read and it's much longer. So many people, you know, it's not something you'd read on a holiday, but many people felt like, wow, so this shows us that math can be put on a rigorous foundation. The kinds of concerns that Russell himself raised about the paradoxes of set theory and you know, what assumptions can we use, these have all been rigorously answered in this book. And all of math in principle follows from this purely logical edifice, which of course no human being except Bertrand Russell can read, but that's okay. Well, Kurt Gödel comes along, and it's 1929, and he's also very influenced by Hilbert's program. Hilbert's program was to show that you can prove the consistency of all of math using only very weak assumptions that he called finitary. And certainly piano arithmetic would incorporate all those assumptions. Okay, so let me give you the contemporary formulation of Gödel's second incompleteness theorem. The contemporary formulation of Gödel's second incompleteness theorem is that if piano arithmetic is actually consistent, so we've been talking about piano arithmetic, you know, it's just the standard arithmetic of the natural numbers. If it actually doesn't prove a contradiction, then it can't prove that fact about itself. So here's why that's important. There's two reasons. First is it shows that contrary to Principia Mathematica, there are truths that don't follow from any established axioms, including the axioms of Principia Mathematica, because you can run exactly the same argument for those axioms. And in fact, Gödel's paper was a response to Principia Mathematica, not piano arithmetic. So in fact, there's a statement that, you know, you can formulate in the language of Principia Mathematica that codes its consistency, or a first order reformulation of Principia Mathematica that says Principia Mathematica is consistent. And if Principia Mathematica is consistent, it can't prove that, and it can't prove its negation. But similarly, this sinks Hilbert's program, because if arithmetic can't prove its own consistency if it's consistent, then certainly no finitary theory can prove the consistency of all of math if it's consistent. So that's Gödel's second incompleteness theorem. And in a way, the second incompleteness theorem is the more important one, because the first incompleteness theorem just says there is a sentence that if, a given theory that interprets arithmetic is consistent, can't prove, and it can't refute. But the second incompleteness theorem is saying, moreover, there's a sentence that is a mathematical coding of the claim that the theory is inconsistent. That claim has this feature. So it's not just that there are some claims that are always left open and unresolvable by anything worth calling a set of axioms that interprets or encodes enough arithmetic. Among the sentences that the theory can't settle is its own consistency. So that's why it's important.
So does it actually shake the foundation of mathematics in some way?
Yes. I mean, this is a matter of controversy, and there's two issues that I'll mention that are controversial. One is, you might say, like, why would you ever have thought that a theory like piano arithmetic or ZFC set theory or some first order regimentation of Russell's type theory, or any theory that could serve as foundation for math, why would you have thought it could prove its own consistency? After all, if the theory is inconsistent, it'll prove anything. So it'll in particular prove that it's consistent. Like, the last thing you want is a theory proving its own consistency. That looks awfully suspicious. So you might think, like, the fact that a theory doesn't prove its own consistency certainly shows that it's incomplete. So it doesn't have this feature that for every sentence in its language, it settles it or its negation. But it's not something that should in any way shake your confidence that the theory is consistent, if you're confident that it's consistent. So one view is indeed that that Gödel's theorem is important because it shows that we can't ever sort of complete math in a formal system. But it's not important because it doesn't show that we should be dubious of any ordinary theorems. On the other hand, Russell's paradox gives you some reason to think that's not a very satisfying response to the second incompleteness theorem, because there are things that we didn't just believe, but took to be logical truths, which turned out to be inconsistent. And this was Hilbert's point of view. I mean, we really don't want to just sit tight and say, so far, no contradiction. I mean, suppose that the shortest proof of a contradiction has more lines in it than there are particles in the universe. Well, then there's no wonder that we haven't discovered that proof of the contradiction, but math would be inconsistent nevertheless. So it would really be nice to have a consistency proof. And Gödel's telling us that it seems like that there is going to be no interesting consistency proof. Now, I say it seems like because the second issue is there's subtleties with the second incompleteness theorem that make it a little difficult to figure out exactly what it means for the purpose of proving the consistency of math. And I won't get too into this because it's a little bit technical, but the short version is there's different proof predicates, which are the predicates in the language of, in this case, arithmetic, that represent proof in the theory. And using standard proof predicates, it's indeed the case that if arithmetic is consistent, it can't prove that it's consistent, and it can't prove that it's not consistent. You just can't settle the question if the theory is consistent. But there are what's called non-standard proof predicates. And a guy named Rosser, for example, who actually gave us the contemporary formulation of Gödel's theorems, he's the one who refined the theorem, gave us a non-standard proof predicate. And there are non-standard proof predicates for which it's the case that if arithmetic is consistent in that sense of consistency, then you can prove in the theory that it's consistent. So there's a question of what kind of proof predicates are the kinds we should care about. And another complication is some people say, it's often said that you can't prove the consistency of arithmetic, say, except by using stronger theories. That's actually not true. What's true is that any proof of the consistency of arithmetic would have to either be stronger or incommensurate in strength. So Gentzen, in the middle of the 20th century, famously proved the consistency of arithmetic using what's called transfinite induction up to a particular ordinal, but with fewer predicates than there are in the language of piano arithmetic. So in one sense, it's stronger than piano arithmetic. In another sense, it's weaker. And so what to make of that kind of proof of the consistency? So the answer to your question, should it shake our confidence in math, is controversial. It's that, you know, it's another one of these, unfortunately, there's not just an experiment you can do or something that you can prove in any interesting sense of proof to settle the question. It's a philosophical matter of controversy. Some people think it does greatly impact the epistemology of math. For example, Edward Nelson, who I told you wrote the book Predicate of Arithmetic. Other people think that, you know, the worst thing you'd want is a theory saying it's consistent. That would be great evidence that the theory is inconsistent, because a theory that proves everything will always prove its own consistency. So you should be highly dubious of a theory that proves its own consistency. But this is, I mean, you know, this is a deep issue, and there's no settled view.
So that means in case that we are forming a kind of a system, arithmetic system, first we need, as a mathematician or somebody who's framing that, first we need to find out that whether that system is consistent or not. Without proving the consistency, we cannot go ahead with that kind of a theorem or that kind of a system. Is it that?
That was kind of Hilbert's point of view, right? That was kind of Hilbert's point of view, and Gödel's theorem is certainly seems to be saying that's not possible. I say certainly seems to be because there's this proof predicate issue.
Right. Thank you.
And yeah.
Just a quick question. I know I'm taking a little bit of your time, but it's so interesting.
No problem.
Rajavardhan is also asking that can probability be used in morality to come with things like this thing is 70% right, etc., etc.?
I mean, sure, probability can be used in all sorts of ways in morality, but it's not that helpful unless at the end of the day the moral framework you land on just gives you a imperative to do the thing or not. I mean, in any given circumstance, you either got to do the thing or not do it. So to be told, for example, that, well, you 49% ought to do it. Well, I mean, okay, now what to do with that? I got to either do the thing or not. So, so action, unfortunately, is an all or nothing affair, and that makes morality tricky in this way. It's you know, for better or worse, we're left either doing actions or not doing them. So whatever moral theory we arrive at, it better issue in all or nothing imperatives to do the thing or not. But probability can certainly play a role in the process of getting us to those all or nothing statements. Yeah.
Okay. One question, Professor. I would like to ask you that is this mathematics that we are talking about is invented by humans as a tool for understanding the world, or is it discovered as an inherent structure of reality?
Yeah. I mean, this is very much back to the question about whether infinity is a concept, right? I mean, I said that, well, whether infinity is a concept seems to go the way of our numbers concepts, because there doesn't seem to be anything that special about infinity. There are things that you could doubt about the argument I gave there, but I mean, that's a thought you could have. The more general issue, right, is math invented? Is math coming from us? Is it something about the conceptual apparatus we bring to the table, or is it something about the table? Right. And the tricky thing is to say, how it could be only something we bring to the table. Because after all, we need to distinguish the world from our conceptual representation of the world. But any statement about the world, any conception of, sorry, not conception, any characterization of the world is going to be up to its ears in math. I mean, what story of the world, of literally the table right here, do we have that doesn't use a bunch of math? It's a bunch of physics. And that uses a bunch of math. So if somebody says, well, here's my view of things. I think that the physical world is real, but I don't believe in any of the math. Well, what does that mean? I mean, you got to then give a surrogate for physics that uses no math. And, you know, the people who are willing to put their money where their mouth is on this do try to do that. So Hartree Field, for example, he was actually my dissertation advisor. He famously actually tried to put in the hard work of starting this process, but it turns out to be very, very hard. And there are people who continue to try to build on Hartree's work. My own view is that it's not gonna succeed in a way that's really satisfying. But to answer your question, I don't see a way to say that math is invented unless you just think the world is invented, right? And that's the tricky thing. You don't want to say the world is invented.
Absolutely. Churamani has got a question. Is there any topic in math which has no physical interpretation, non-intuitive, and is only abstract?
Yeah, I mean, the main discipline. So first of all, I should say that there's a famous history, of course, in math. I mentioned it already when talking about Hardy's book, A Mathematician's Apology, of the pure mathematicians doing something, and then it only much later finding application. So, you know, for example, Riemann's differential geometry, and Einstein then consulting his friend Grossman, and Grossman, you know, saying, hey, actually the mathematicians have a tool for you for general relativity. It's called differential geometry, and it'll do exactly what you need. So there's certainly a history of what seemed to be math that has no relevance to the physical world, finding relevance to the physical world. However, there is one branch of math that really does seem to not only not have relevance to the physical world, but it's hard to imagine how it could come to have relevance to the physical world unless we're really wrong about what the physical world is like. And that is indeed transfinite set theory, the theory of infinite sets, the theory of the theory that Cantor invented. So, you know, there's work on what mathematics is needed for science. And I mentioned a minute ago the limiting case, the idea that maybe no math is needed for science. Maybe you could rewrite all of math or reconceptualize, not of math, of all of science in a way that only talked about physical things. This is something that Hartree Field tried to do. But, you know, for my money, I don't think that's going to work. And so if there's some math that's needed, how much for science? And Solomon Pfefferman did a lot of work on this, and he was inspired by Quine, the philosopher I mentioned earlier, who had a more sophisticated empiricist conception of math. And his final point of view was pretty radical. It was at first approximation, all you need is a system that Hermann Weyl came up with in the early 20th century called predicative mathematics, which you know, it doesn't even countenance ordinary calculus. It doesn't even countenance like the least upper bound principle. But Pfefferman went further and argued that actually all you need, using an argument from proof theoretic reduction, which I won't go into, but he argued that all you need at the end of the day is actually just piano arithmetic. So if that's right, then nothing beyond piano arithmetic is actually physically real. Now you don't have to believe Solomon Pfefferman to think that even if a lot of math like calculus and the theory of manifolds and Hilbert spaces and so on, even if that's all real, the theory of, for example, large cardinals, which is a subject of set theory, so very strong axioms of infinity, that's not physically real. That's something about us. But as I say, there is this history of, it's always hard to be sure, because there's this history of Baroque and recondite objects coming to find application in the physical world. And by the way, I should mention, this is the same with philosophy generally. Philosophy, people always make fun of philosophers for, just worrying about things that have no application. But there's a great book actually by Scott Soames called The World Philosophy Made, about how, philosophers worry about X and Y and Z, and then 50, 100 years later, X, Y, and Z ends up having direct application to some physical or otherwise tangible subject. And it ends up, spawning its own science. And now we call this subject, computer science, say. The computer science, as we know it, was, it was founded originally on the ideas that Frege was working with when he was asking the Baroque question, the ivory tower question: what is the number 2? What is the nature of the number 2? And that gave us this whole theory of formal systems. And eventually Turing comes along, once again thinking about abstract mathematical ideas, Turing machines. That gives us real life computers. Real life computers give you your iPhone eventually. So you never know where things are going to go. But if I had to put my money on an area of math that just really is going to stay pure, that's transfinite set theory, which we normally teach in the philosophy department, maybe for that reason.
Right. Last two questions, Professor, before we end. Now, in the general area of teaching mathematics, say for example, we always come with comparisons. I mean to say, for example, if you're teaching vector calculus, vectors are arrows. In fact, we know that vectors are not actually arrows. They are part of the abstract vector space. In case of, acceleration, momentum, even for gravity, etc., we try to compare all those, things with some analogy or etc., in order to make a better visualization, so that at the initial the students can understand. But as a matter of fact, we understand this is required at the primary level. But as we mature, we also understand that is not correct, because mathematics is a language by itself and it carries its own sense. So my question to you would be, do you consider that at the initial level, these type of analogies or comparisons creates a kind of an impact, or should we stop and try to, make the students think right from the beginning in terms of the abstract nature, not in terms of something concrete?
Yeah, I mean, so here I'm actually going to go against my own people, I think, a little bit. So there's a debate in math, mathematical methodology, about what counts as a proof. And what I mean by that is, where does the buck stop? And the standard view is given to us by the philosophers Frege, Russell, and others, which is that a mathematical argument is a proof if it could, in principle, be translated into the language of first-order logic, and there's a derivation in that language from the axioms of ZFC, perhaps with small, large cardinal axioms, such that every line of that is either an axiom or follows from the previous line by a rule of formal inference of first-order logic. And then you could feed that string of symbols to a machine, and the machine could tell you after a finite number of steps whether or not that sequence of objects is a proof. But of course, nobody thinks like that, right? I mean, if you were to read that, I mean, a great illustration is the Principia Mathematica, again, which is still not completely rigorous in this sense, but it's very rigorous. And I mean, Russell famously complained that thing damaged his brain writing that book, because we don't think that way. We don't think in terms of, symbolic representation and what's the formal next step and so forth. We think in terms of analogies and intuition, and one talks about like what's the key idea of the proof and stuff like this. and so there are people, these are heretics, but there are people in the mathematical world who think that the buck does not stop with the philosopher's notion of proof. Proof is something that is ultimately human, and there is no higher authority. And if you were to if all the mathematicians agree, I guess the view is that that's a proof, and if they don't, then until we can find something that they all can sort of agree on the intuition to, you don't have a proof. Now that's an uncomfortable, I think, position to have, but something I think that's true about it is that we're human beings, and the point of math is to communicate ideas to humans. So, something you do an excellent job of with your lectures online is to convey the intuition. And the intuition is where you have to start, I think, to make progress. I mean, the great geometer Bill Thurston, he would often publish his work in sort of not very rigorous ways. His famous book on low dimensional topology is not rigorous. It's quite intuitive, and he did that intentionally. He had the rigorous proofs, but he did that intentionally because he wanted to communicate the ideas. Human beings were reading that book, not computers. So my own view, this is maybe goes a little bit against the philosophers who are so obsessed with just a level of rigor that's quite unusual, even in pure mathematics. My own view is that intuition is if it's not the most important thing, it's one of the most important things. And you can't get intuition without analogy and pictures and metaphors and so forth. So I don't see it. I don't know what Bourbaki's view would have been, but I don't see it as some kind of corruption or something of mathematical rigor. I think mathematical rigor is a downstream activity, and the first thing you need is intuition.
Absolutely. So just to tell the viewers that Professor Justin was referring, and we came in contact when Professor Justin found some of my videos in quantum field theory and differential geometry very interesting. And now I can really understand, because being a professor of the philosophy of mathematics, what he is trying to make out from my lectures, because they are not truly rigorously mathematical, and my idea has been basically to give you an intuitive idea so that people can get hold of the overall concept, because math, you will find a huge amount of mathematics in different books, but analogies and this type of comparisons are. So I am happy to distribute my videos in PDF format to Justin, and I think you are making a good use in your University of Columbia. I'm so glad to do that. My last my last question would be, I know it's going a little bit over the time, is that I think, Professor, you have heard about the famous meeting between Einstein and Tagore, which took place on what is called the nature of reality. There was one meeting which took place between Tagore and Romarola, who was a French philosopher, but this was between Einstein and Tagore, when Tagore, the famous Nobel laureate from India, traveled to Kaput in Berlin and met Einstein. I will pass on a video lecture which I have made. It is called On the Nature of Reality. And it basically talks about the philosophy of reality and mathematics. Now, I will pass on the lecture. It is on a series of 3 lectures. I'm sure you're going to enjoy that. It is basically on the philosophy of reality. Now, my question was that I understand from the conversation of Einstein and Tagore that they really could not understand each other, to be very honest, if you take my cards, which was much better on the scale of Romarola, because Romarola, being a philosopher, pianist and a writer and a Nobel laureate, so both of them went together. Now, what Einstein and Tagore, when they met, the basic idea was called On the Nature of Reality. It was published in New York Times. Now, what Einstein was telling is that, for example, this is the table, right? And I'm closing my eyes right now. So the table does not exist. Obviously, if I am not there, the table does not exist. Now, what Tagore was telling, Rabindranath Tagore was telling, that the table do exist even if you close your eyes, because the
Right.
reality is not what I mean to say, what you think. I mean to say, what you
Right.
see right now. He
Right.
gave an example, the famous Apollo Belvedere, that is being framed by humans. What you were telling, that it is framed by human. So if I cannot see the famous Michelangelo statue, or if the table, then the table surely does not exist, because all the reality is within me. On the other hand, Einstein was telling that it doesn't matter whether I see or you see or even we do not see,
Yes.
but the table
Mhm.
exists as a part of the reality. Any
Mhm.
views, Professor? What do you think of this part?
Yeah. Well, so just 2 points. One point is this debate is just the debate between what's called in the history of philosophy realism and idealism. So this goes back to antiquity. It's not a new debate, but the idealist thinks that that reality depends on our minds, and there are sophisticated advocates of there have been sophisticated advocates of idealism. A good example would be Bishop Berkeley, the guy who came up with a great criticism of the calculus and ultimately compelled the mathematicians to come up with the epsilon delta definition of limits and so forth, rather than making use of the infinitesimals and fluxions of Newton and Leibniz. But this is a long-standing debate, but it got traction and interest. This is the second point, in connection with the Einstein-Bohr debates, because Einstein famously argued, that, I think the way he put it is, the moon is there even if you know it or not. I mean, but the more general issue was about how to think about the EPR experiments, and there were some pretty out there philosophy. There was some pretty out there philosophy being done by the Copenhagen school of quantum mechanics, and Einstein and Schrodinger in particular really felt like this has gone off the deep end. I mean, this is that I don't know whether they made the connection with just the old realism idealism debate, but what certainly what people like Bohr and Heisenberg sounded like they were saying at times is that, the moon wouldn't be there if I wasn't looking, or if I go to sleep, the moon goes away. And of course, the right thing to say is, it's not that the moon goes away. My perception of the moon goes away. My idea of the moon goes away. My awareness of the moon goes away. But the moon doesn't depend on me and doesn't care about me. The moon is a planet that exists totally independent of me. So one needs to distinguish their perceptions of things from the things that are perceived. So, Michelangelo's Sistine Chapel or whatever, on the one hand, there's the Sistine Chapel. On the other hand, there's my perception of the Sistine Chapel. Now, I want to say all that just to advertise there's the generic realism idealism debate, and that's what I'm talking about. But there are some interesting pressure points in light of the no-go theorems in the 20th century, Bell's theorem, the Cauchy-Specker theorem, and so forth, to do with the Einstein-Bohr debate. So there's like a way to make this debate a little more interesting in light of the no-go theorems in quantum mechanics. And so an iteration of this debate was then the development of different interpretations of quantum mechanics. You can sort of think of Bohm and the Bohmian interpretation of quantum mechanics as the neo-Einsteinian view that the world doesn't depend on us. There's no collapse of the wave function in the sense of observation making reality come into be. But by contrast, there remain views where collapse of the wave function is a physically real thing, and that makes the world dependent on our minds. I mean, that's an interpretation of quantum mechanics according to which something like idealism is true. the important point, I think, just to keep in mind with all of this is that this is high philosophy, right? You can think that somehow physics is resolving these questions just by experiment. There's no avoiding the philosophy. You got the experiments, but now you got to do the philosophy. Are you going to go the direction of Einstein? Or are you going to go the direction of Bohr? That's not something that the experiments settle, evidently, because they knew all the experiments and they disagreed fundamentally about things, even like whether the moon is there when I go to sleep. So these are very basic philosophical issues, and that's why it's so important to have the cross-pollination between philosophical discussion and physics, just like with math.
Absolutely. So thank you, Professor. I think that you enjoyed today's show with a lot of.
It was great, yeah.
And I will definitely pass on to you the Einstein-Tagore debate. I think that would be a wonderful thing, because I have I don't have the time. Otherwise, I was thinking to ask you a few questions on Wittgenstein's philosophy also. But surely what we can do is that, yeah, we can schedule some. Yeah, we can do it some other time, another day when you are free, because this is an ocean, and I think that it requires a series of podcasts to complete certain basic things. So you can watch that one, because I have also taken from Heisenberg and Bohr Einstein debate and certain I would say Indian philosophers merged with Einstein's theory. I think this is the right cup of tea for you in the morning, which you can enjoy. So any message for our viewers, subscribers, anything for me, or whatever the way you want to conclude?
Well, thanks so much for having me, and thanks everyone who is attending. I mean, this is such a great program you've got. So I hope it keeps growing. I hope I'm loving how you're bringing people in from so many different academic fields, and
absolutely, because this is a subject which is not much discussed or debated among people, especially the philosophy of mathematics. And I am earnestly willing to bring people, professors around the world to speak on this subject, because this really requires attention, and it really requires to magnify so that people would know and talk more about these things. So thank you, Professor.
Yes.
Wishing you a good Sunday ahead. I know it is morning and you must be hungry because you didn't have the breakfast.
I'm okay. Thanks, but thanks a lot. It's so great to talk.
Thank you. Everybody. Thank you very much. Goodbye. Yeah, bye.
Bye.